This is lecture number 17 of the course AU 203 Statistics and Quality Control. We have already talked about Poisson distribution in the previous lecture. Today we are going to see the expected value or mean value and the variance of the Poisson distribution. Let's see, the content is, we will start with looking at the shape of the Poisson distribution, and then we will go into the calculating the expected value or mean value of Poisson distribution, and then we will calculate the expression for rather deriving the expression for variance of Poisson distribution. And then we will look into calculating probability and visualizing the probability distribution of Poisson distribution in Minitab. And in the end, we will look into discrete distribution in Minitab. So any distribution other than binomial and Poisson, if there is any other distribution which is represented through a probability mass function, can be deal in Minitab. How to deal in Minitab? Okay, so let's say if x is your random variable which is following a Poisson distribution, and your average rate of occurrence for a given period or a given area is unity, then you have this typical distribution where the probability of getting your value of your discrete random variable 0 is some higher value, and 1 is also some higher value, and then the probability starts decreasing to value 2, 3, 4 and 5. So as the number of value of the random variable is increasing, its corresponding probability is decreasing. So this is a typical distribution in this Poisson distribution. We see that, okay, let's say if the average rate of occurrence increases from 1 to 2, then the distribution shape of the distribution changes. And let's say if we increase further your random variable 3, then the distribution shape of the distribution is so now you have some smaller values have lower probability, and higher values have smaller probability, and some middle values have higher probability. And once you further increase to 5, and then you see, so what is actually the pattern you found, that the shape of the distribution is actually depending upon the parameter. So if a value of the parameter changes, the shape of distribution would be different. And we have seen that as the parameter value of the parameter is increasing, the shape of the distribution becomes from asymmetrical towards symmetrical, or becoming a normal distribution. Okay, so mean of the distribution or the expected value of the distribution, let's say we have a random variable x which is distributed having a Poisson distribution with a parameter lambda. So its corresponding probability mass function would be this one. So probability mass function is nothing, just a mathematical function. If you give certain value of a random variable small x, then it gives you its corresponding probability, and your x can take any value, any discrete value. So because it's a discrete probability distribution, so x can only take discrete value. X cannot be 0.1 in this distribution. We are interested in an expected value, so we know the definition for expected value of any random variable is simply the score of that value multiplied by its corresponding probability and take the sum. Then we will be able to calculate the expected value of a random variable. So we have a random variable and its corresponding probability function, then we will be able to calculate the sum. So I just have x here, and this whole probability function is there. So if you will be able to evaluate this series, we will be able to calculate the expected value. So there is some mathematics in evaluating this series. Let's say at this point what I have done is, if I take x key the value of x0, then 0 factorial would be 1, and the whole thing multiplied, so the first term comes out to be 0. So what I do is I start my series instead from 0. We start our series from the value x equal to 1. So here when your x is 1, then you have 1 factorial, and so on. So in the second step, what I do is I take the common deliberately, because e to the power minus lambda has no value of x associated. So I take it common. So e to the power minus lambda is taken common, and we end up with the x here and lambda to the power x and x factorial. And then we have to make a simplification, because as we know, x factorial would be x into x minus 1 factorial. Then x and x would cancel out, so you end up with only x minus 1 factorial. Okay, in the next step, we take a deliberate common of lambda, because lambda is here, lambda to the power x, so I take it a deliberate common. So e to the power minus lambda, and lambda is a common now. So if you multiply this thing, you are going to end up with the same expression. And then we take a substitution. It is x minus 1, it is x minus 1. So instead of dealing with x minus 1, we just substitute y equal to x minus 1. Then our expression would be in terms of y. And keep in mind, we need to change the limit of the series as well, because when x is 1, 1 minus 1 is 0, then y becomes 0. So not just change the variable, but substitute the limits of the this summation series. So y here is 0, because when x is 1, 1 minus 1 is 0, then y come out to be 0. So you end up with lambda to the power y and y factorial. Okay, this expression, this term in this sigma notation summation, if you this is in standard result, and you can expand that series by bringing first y0, then y1, and then end up together up to infinity. So you will end up with a number called e to the power a. So the whole thing is become e to the power a. Okay, then expected value would become e to the power minus lambda into lambda, which we have taken common, and then the whole thing in this sigma notation would be because it is e to the power a is your base, and here the base is lambda, so e to the power base is lambda here. So that's why the whole thing can be written as e to the power lambda. Okay, now we know e to the power minus lambda and plus lambda, if you add them together, it would be e to the power 0, and e to the power 0 into that would be 1, and 1 into lambda would be lambda. So the expected value of a random variable in the Poisson distribution is nothing, just the parameter lambda, which is itself is actually representing the average rate of occurrence in the distribution. So the expected value is nothing, exactly the same as equal to the value of the parameter, which is the rate of average rate of occurrence. Okay, we can apply the definition for this Poisson distribution. We know the definition for variance of a random variable is nothing, how the score varies with the mean value, and if you take the square and calculate the expected value, you will be able to calculate the variance. So what we have done is we have just simply do the same thing, just substituting the expected value, and there is an alternative formula for calculating the variance. We already have learned this is a first way of writing down, and this is an equivalent way of writing down. So instead of dealing with the difference of the value with the mean, if you take the square of the random variable and subtract it with the whole square of the expected value of that random variable, we will be able to calculate the variance. So using this definition, it would be much easier to calculate the variance. For example, as we already know, the expected value of a random variable is we know the expected value of a random variable, which is actually equal to the parameter lambda. Now we can calculate the expected value of x square, so that we can calculate the variance. So expected value of x square is nothing, just the formula for expected value is x times its probability. If it is x instead of x, if it is x square, then just substitute x square here and corresponding probability, and then we will be able to solve it as we have solved for expected value of x square is this expression. Okay, what we can do is If we have another function x times x minus 1, then it would be, the expected value would be equal to this x times x minus 1 into its corresponding probability, and take the sum from x can take value from 0 to any value infinity. Okay, so here expected value of x can be written instead of limit 0, we have taken it a limit 2, because once it is 0, so the whole term would be 0. So it is not going to make any difference in the summation, because the 0 plus some value would remain the sum value. So that's why we make it a limit 2. Once we make it a limit 2, 2 minus 1 would be 1, and even if it is x is 1, then 1 minus 1 is 0. So the whole term, whatever this is, but the whole term becomes 0. So 0, if added in some other terms, it won't make any difference. So instead of writing down the limit 0, I take the limit 2 here for calculating the expected value of the product of x and x minus 1. Okay, and now I take a deliberate common e to the power minus lambda earlier, as we have taken it in the previous calculating the mean of that x times x minus 1 into lambda to the power x over x factorial, and then we need to make it again, writing down again, and then I take a deliberate common lambda to the power 2. Earlier we have taken lambda to the power 1 common, but now we have taken lambda to the power 2 common. So we have e to the power minus lambda and lambda square common, and the rest is here. And always do this step, multiplying this term with this term. If you are getting the same, then it means your deliberate common step is correct. Otherwise it won't be correct. You always need to check that. Okay, now I can make a substitution here, y is equals to x minus 2. So once you put x equals to 2 here, then y becomes 0. So your limits are y equal to 0 here now, and whole x minus 2 becomes y, and this would be y factorial. And the whole thing, as we already know, a to the power y, and our a here is lambda. So lambda to the power y would be e to the power lambda. So the whole thing in this sigma notation would be e to the power lambda, and this would become expected value of this would be lambda square. And here what I can do is just knowing the rules for expected value of a random variable, we can multiply this, and that would be the expected value, and expected value is actually, we already know, equal to lambda. Then expected value of x square would be equal to lambda square plus expected value of x, which is lambda. Okay, now I can substitute here in this expression to get the variance. So I just substituted the whole thing in this expression. Then expected value of x square would be lambda square plus lambda minus lambda whole square. So what eventually comes out to be the variance of random variable in Poisson distribution comes out to be the same as the lambda parameter. So Poisson distribution is a very special distribution in which it is a single parameter distribution. Its mean is exactly expected value is same as the value of the parameter, and its variance is also the same as equal to its parameters. So it is quite easy to calculate the mean and variance of the Poisson distribution. And then we can look into this standard deviation. As we know, the standard deviation is the square root of the variance. So if we have to calculate the standard deviation sigma, which is the square root of the lambda, whatever the lambda is, if lambda is 4, then its variance would be 2. So this is how we can calculate the mean and variance of a random variable. Okay, now we'll go into doing it on a Minitab. So we will solve directly on a Minitab. I will go swift to Minitab as well. Okay, now we will see how to calculate probability for a Poisson distribution using Minitab. So if you just look at the problem we have done in the class, this problem in which you have a Poisson random variable where the parameter or the average rate of occurrence for this problem is 4.6, and then we have to calculate this 16.3% the probability, and draw the probability distribution for that. So we can do it in this way. Let's say we go to this mini tab and calculate probability distribution. So calculate probability distribution and choose here the Poisson distribution. If I choose the probability, let's say I'm interested in calculating the probability, and the mean value, let's say here is 4.6, and my input constant is, let's say I am interested in calculating when your random variable is having a value 3. So on the mean I put 4.6, and the input constant I put x equal to 3. Once I click it, that I will be able to see the corresponding probability in the session windows. So for the Poisson with mean value of 4.6, so its corresponding probability is 16.308%. So this is how we can calculate the probability, and we can visualize the probability, and we can calculate exactly in the same manner on the graph as well. For example, probability distribution plot. So if I go to this probability distribution plot, I have an view single probability distribution or view probability. Let's say if I'm interested in viewing, calculating the probability and view the probability, or just view distribution. Let's start with this distribution. I first need to select the distribution, and the distribution here is the Poisson distribution, and let's say the mean value is 4.6. So once I select that, I will be able to see that distribution. So I can see that 4.6, it has a maximum probability, and probability plot looks like this thing. So I can get this probability distribution with the mean value of 4.6. So I can see this exactly the same distribution. I mean, I have drawn here the bar chart for that, but exactly actually the same thing is the maximum value is an order of 0.2 something. So I can see the same thing here is an order of 0.16 something. So I can get a probability different values. I can see this distribution as well. So this is how we can calculate probability for any value. Let's say here the probability is not calculated. Let's say I'm interested in calculating the probability. Then I go view probability. Let's say I just view the probability and go to this Poisson distribution, and the mean value taken here is 4.6, and I'm interested in the x value. For example, my x value is 3, and either a left tail test or a right tail test. Let's say I'm interested in the value 3 to 3, or anything greater than 3 or less than 3, whatever it is. Let's say if I just do this, so let's say you see here 0.1613 is actually the probability for the value of x equal to 3, which is plotted in this red bar. So this is how we can see the particular probability using this graph tab. And okay, after this we can I would like to show you some other thing, like we have seen it in the lecture. Let's say we have such a distribution. Let's say I have this distribution which is not a Poisson distribution, which could be any discrete distribution, and W is a random variable we have, and its corresponding probability is this. So how to read by the mini tab is you can do it. Let's say at -3, -2 to 1 is their random values. So just I say W is the variable where value is -3, -2, -1, 0, 1, and 2. And let's say for this value, the corresponding probability is known to me for that random variable. Let's say its corresponding probabilities are 0.1, 0.25, and 0.3. So I just put it 0.1, 0.25, 0.1, 0.25, 0.3, and the rest is 0.3, and then 0.15 and 0.12. 0.15 and 0.2. Okay, so okay, we don't need to go up to 2, just from -3 to 1. So let's say this is my discrete probability distribution and you need to take the sum of this value, and that sum comes out to be, for example, let's say I just calculate the sum of all the probabilities, just take it out from this calculator and store result in, let's say, C4, and what the expression is, taking the sum of values which is given in C2. I need to take the sum, and I can see that the sum of all the values in that probability comes out to be 1. It means this is something a legal probability distribution, because if sum of the probability is not equal to 1, then it won't be considered as a legal probability distribution. So here it is a valid probability distribution. What I can do is I can calculate the probability for any value of this, or I can show the graphically this probability distribution. Let's say if I am interested in showing up this probability distribution plot of that, or calculating the probability. Let's say I just want to view single, I want to view this, and here because it's a discrete distribution, so I just choose here a discrete distribution, and the values are given for that random variable is in W, are these values in column 1, and their corresponding probabilities are in column 2. So this is something I have read these random variables and their corresponding probabilities from this tab of choosing the discrete probability distribution. I just click it, so I will be able to see this distribution. When it is x0, then your probability is 0.15. So I can see that probability, and if it is it is 1, then this is the probability. So this is how I can give an input here to calculate the probability. Let's say, for example, I am interested in calculating the cumulative value of that. So let's say the cumulative value is represented by f of w, and I'm interested in this column 3 to calculate the cumulative. So I just go there, calculating probability distribution, discrete probability distributions, and I'm interested in calculating the cumulative probabilities. And my values would be w, and my corresponding probabilities are in this, and I want to store input in the C3 column. Actually, I wanted the storage to be in this C3 column, so all the cumulative values would be shown here. So once I do that, okay, I need to input column. Okay, input column is this, and the optional storage is this. So for every this random variable, this cumulative value, cumulative probability would be stored in this. So here you see this cumulative value is stored in that, so 0.1, and 0.1 plus 0.25 is 0.35, and 0.35 plus 0.3 is 0.6, and 0.65 plus 0.15 is 0.8, and 0.8 plus 0.2 is 1. So obviously you are moving from 0 to 1, and you will be able to draw this cumulative frequency curve if you plot these values. So this is how we can deal with the discrete distribution. We can calculate any cumulative frequency or something, let's say, and this is how we can deal with this discrete distributions. So this is where I stop here.